Okay, let's start. Oops, how do I turn? How do I make the screen bigger? 1 moment. Video. The thing is, I haven't even installed any PDF editor yet. Or what do you use for the PDF editor at the moment?
Oh, I changed. Before I used Acrobat, but now I use Manual because
So, okay, I haven't even downloaded it. So, okay, let me share this screen, okay? Then let's look together.
Sumatra PDF. It is like free. Sumatra
Okay, yeah,
PDF.
please share with me, then I'll take a look.
I don't know what's happened, but in Acrobat, my license is broken and they became annoying, and I just changed to Sumatra.
Yeah, I mean, all these apps, at some point, they want you to buy it, right? Sooner or later.
But Sumatra is free, so I just choose this one.
I see. Let me see. Why do I have so many many tabs? Okay. Okay. So let us go to maybe some slide we looked at last time. Maybe it's around here. Okay. Okay, so let's take a look. Will I be able to write this time? No? Oops, cannot write. Oops, okay. Okay, let's look together. So, as you know that the EPB often occurs, right, during equinoctial months, for example, and sometimes they occur right after the geomagnetic storm, or maybe there's some suppression, right? So when people talk about the EPB, there are two types. I mean, there are different types of EPB, but according to the occurrence period, people sometimes look at two types of EPBs, such as post-sunset EPB and post-midnight. So the post-sunset EPB, so these normally occur during equinoctial months, and it's just right after sunset. Sometimes, about a few hours after sunset, for example. So, especially during solar maximum period, they have more and more frequencies, right? For this type of post-sunset EPB, the phenomenon that is often mentioned to have a great cause is the PRE, okay, which is pre-reversal enhancement. It dominates the EPB. Okay, in the old literature, some people interchange between ESF and EPB. So if you see some papers in the past, they talk about equatorial spread F, that they also mean EPB. Yeah, so it seems to be quite common to sometimes interchange, right? Yeah, and but you know that ESF, or equatorial spread F, is more like the observation from the ionosphere, which is more at the bottom side, right? But EPB itself, it's the phenomenon, right? But ESF is a type of observation based on ionosphere. So it can see some traces of plasma drift, plasma disturbance, and all that, but only to certain height. Yeah, but when we talk about EPB, sometimes it goes all the way up to, or irregularities, it go all the way up to 1,000 kilometers. And for that type of altitude, the ionosphere cannot penetrate all the way up because it observes the bottom side, the bottom part of the ionosphere, right? So yeah, be aware of that. And then there's the other type based on the occurrence period is called post sunset, EPB. Yeah. So post sunset is not well understood actually. Yeah. So if you observe the occurrence of irregularities, sometimes you see post sunset and then disappear. Let's say 10 p.m. and then suddenly you have more EPB at midnight and then last longer. Yeah. So for the post midnight EPB, many literature they often talk about the more higher occurrence, higher frequencies during the solar minimum period, especially solstice months. So and one of the main cause is related to what is called gravity waves. Okay. If you remember back before this, Pinmason had some presentation. Yeah. So gravity waves is one of the important factors related to the EPB. And if you remember from Pinmason's work, gravity wave when researchers study, what they do is they study the what is called the gravity wave coefficients, which is based on using wavelet transform on the FOF2 signals. Yeah, and then you can get some coefficients and then compute gravity waves from there. And anyway, and one of the some of the research paper they I think particularly from Nagoya University, they talk about occurrence rate of the post midnight EPB that increase with the decrease of solar flux. Yeah. Okay. And well, what are some effects of plasma bubble? I think you have seen already in many presentation, right? That with the irregularities, you can have the differences between you know sometimes you have a low plasma density, then you have high plasma density. So the difference is called gradient, right? Like this is quite clear. So this is low density or low delay from ionosphere or low TEC, and then suddenly you have very large, very high values, on two sides or even in other area. So the differences here is called gradient. So it means that if the satellite signals go through the blue area, you get low delay. The same satellite, the signals go through the red area, it has higher delay. So some technologies that rely on two two areas of ionosphere, sometimes you have this disturbance, or not disturbance, the gradients. For example, in Chiba system, what happens is when the airplane is approaching the landing area, right? It receives the correction signals from the reference station at the airport, but the reference station estimate the delay from this path, but the aircraft receive signals on this path, so the delays are different. So the airport, the reference stations on the runway reports incorrect correction. you know yeah. So some technology, because they rely on this type of they rely on this type of spatial information, the gradients become important, right? The ionosphere irregularities also affect the signals, GPS signals that go through these irregularities, because these bubbles is not static. It keeps growing, and it change, it moves. So the signals is affected with on the amplitude, on the phase, and sometimes what we see at the receiver on the ground or on the airplane is called amplitude fluctuation, amplitude scintillation, or sometimes in the middle latitude and high latitude area is called a phased scintillation. because they are affected more on the phase, not on the amplitude, for example. So besides the equatorial region, the mid-latitude also get affected by some of the irregularities. And for example, in Japan, sometimes they see this type of gradients as well, or some disturbance as well. In the mid-latitude, it is often called storm-enhanced density. And this is mostly due to the geomagnetic storm. It's different from the equatorial region. You have both. You have the normal bubbles, and then you have the storm bubbles. So you have both. Yeah. Anyway, so some years ago, back in 2008, there was a study in US about this type of gradient, because at that time they were busy studying about GBAS, and they found that in some area in the US during the storm, you could have very high gradients, exceeding the standard. Yeah. Exceeding the specified standard by ICAO. Yeah. And in ICAO, the standard says that per kilometer, per 1 kilometers, I mean, for the difference of 1 kilometer of two locations, the delay difference cannot be more than 250 millimeters. What is 250 millimeters? How much meters?
Meters, 0.25
0.25 meters. Yeah, cannot between two locations, 1 kilometer apart. You cannot have more than 0.25 meter difference. Yeah, so that's covered by ICAO standard. Because in GBAS, what happens is when the aircraft wants to estimate its position, it relies on different types of noises, and they quantify in terms of sigma square values. For example, sigma square value of the errors from the ground, sigma square error from the troposphere, sigma square, which mean error from the aircraft receiver itself, sigma square error from the iono gradient. So and sigma square value of the multipath, and among others, and sigma square value error of the noise, just noise. So the iono gradient is one of the errors that is quantified, lumped together, all the errors before it can be computed to the position. So anyway, so at that time when they found out about this large value above the threshold, but in ICAO standard, so it created a lot of works or study coming out from that. Yeah. So that's why in KMITL we started doing this study in 2011. 2011, we installed receiver on the E12 building and also at Stanford University, and then we try to quantify this type of gradient analysis. Yeah, because it's a solar cycle, right? So each solar cycle lasts like 11 years, and that's why it took us like many years to collect data from 2011 until now. And now it's 2025, right? So since 2011, now it's still only 11 of 13, 14 years. We have only conducted study only one cycle. It seems like a long time, but it's already just a little bit over one solar cycle. Yeah. But at that time, 2011, that was the increasing trend of the last solar cycle. The max of last solar cycle was 2012 and 2013 around that time. Yeah, so we were right at the tip, right? And then we collect data all the way to the bottom and then now back to the top again. Yeah. So that's why we studied at that time. And we published quite a lot of work. I remember when we first published this type of study, many countries in Asia, like Malaysia, Singapore, they fly to us to talk and discuss. Yeah. But nowadays we already collected one cycle of data. But maybe with more and more research and more in-depth study would be nice. Yeah. At that time, we only did the 1 second interval. However, for aviation, each receiver